differentiation. I would do natural log on the left and natural log on the right. I'm going to do a little bit of algebra cleanup first. I would rewrite that square root as a 1/2 power, and then I would use some log properties to separate these factors. So I could write natural log of x plus natural log of 2x plus 1 to the 1/2. That's using the product rule for logarithms. And then we have a power rule for logarithms, which will allow me to bring that power down. And then I would use implicit differentiation. So to use implicit differentiation, I would do the derivative with respect to x on the left and the derivative with respect to x on the right. And on the left, since the variables don't match, I'm going to need to use the chain rule. So I would do u prime, that's the inside derivative, over the inside, u prime over u, y prime over y. On the right-hand side, the variables do match, so I'm still going to use u prime over u, but I don't have to do the extra chaining with the variable. So the derivative of ln x, the derivative of x is 1 over the inside. Carry down that 1/2, and then I would do u prime, the derivative of the inside would be 2 over the inside. So that gives me y prime over y equals 1 over x plus those 2's cancel, 1 over 2x plus 1. I'll finish solving by multiplying by y on both sides. And y was given in the original problem, and that was x times the square root of x plus 1. The square root of 2x plus 1. And I can continue with a little bit more algebra cleanup if you'd like. You would have, you could get a common denominator over here. That would be 2x plus 1 over x times 2x plus 1 plus x over 2x plus 1 times x. So I got a common denominator. I can combine those fractions together. That becomes 3x plus 1 over x times 2x plus 1. And then these x's cancel. And then because these have the same base, you can combine them together. And this one is this one has the 1/2 power, and you would subtract this one with the first power. So 1/2 minus 1 gives me negative 1/2. So I'm going to put it in the denominator to take care of the negative, make it the square root to take care of the 1/2. And we get that as our answer. So we're going to use implicit differentiation to calculate the derivative on this example. And I'm using implicit differentiation because our equation is written in an implicit form. Explicit form would be if you have y equals and the only variable on this side would be x. Our equation has the x and the y mixed up together. on one side, and it would be a challenge to rewrite this problem in that explicit format. So I'm going to use implicit differentiation to calculate the derivative. So to start that, you would calculate dx on both sides. And then we'll notice that on this left-hand side, the variables match each other, so we're going to calculate the derivative like normal. That would be 2x. And then on the right-hand side, I'm noticing that I have something where I have to use the chain rule. I have one function inside of another function. So I'm noticing that my outside function is this squared, and my inside function is this 4xy cubed plus 1. So I'll start by taking the derivative of the outside function. That's a power, and I'll use the power rule. So I bring the power down, take 1 away from the power. I leave the inside alone, but then I have to chain it by multiplying by the derivative of the inside. So then I'm going to continue. I don't need to write that first power, but I do need to calculate the derivative of 4x squared y cubed plus 1. Inside those parentheses, I have 2 terms. So I want to focus on taking the derivative of the first term and then the derivative of the second term. And this is multiplied by this. That first term is 4x squared y cubed. I'm going to need to use the product rule to calculate the derivative on that term because I have the product of 2 expressions with variables. So I consider this my first term, 4x squared, and y cubed to be, I said term, it should be factor. 4x squared is the first factor, and y cubed is the second factor. So I'm going to use the product rule. So that's the first times the derivative of the second, plus the second times the derivative of the first, and then that last term, the plus 1, the derivative of a constant is 0. Okay, so I'm going to copy some stuff down and continue calculating the derivative. I want to find the derivative of y cubed. Now, I know I didn't write it anymore, but remember, we're taking the derivative with respect to x. And this has a variable of y. The variables don't match, and so I'm going to have to use the chain rule when I calculate the derivative there. So that will be 3y squared times y prime. And then I'll find the derivative of x squared, and there the variables do match, and I take the derivative like normal to get 2x. So I've calculated all of the derivatives that I can calculate. Let me just write this a little cleaner. Let's see, I can multiply the 4 and the 3 together to get 12 x squared y prime plus 2xy cubed there. So I've calculated the derivative, and now what I'm looking for in my problem is where all the y primes are, where all the derivatives are. and I only have this one here, and I want to solve for that, because that was our goal in this problem. Our goal was to find y prime or dy dx. So I want to rewrite the equation so that I have y prime by itself on one side. So I'm going to divide both sides by 2 times 4x squared y cubed plus 1. Okay, so someone just pointed out that I've made a mistake here. Up here, when I was considering 4x squared to be my first factor, I did it correctly right here. I did the first times the derivative of the second, but on the second part, it should be the second times the derivative of the first, so I left off the 4 right there. So there should be a 4 there, and that makes this 8x, and that makes this 8xy cubed. Good catch. So then, okay, where does that bring me? So I've got 4x squared y cubed plus 1. I divided by that on both sides. That cancels this out. And I've got 2x over 2 times 4x squared y cubed plus 1 equals 12x squared y prime plus 8xy cubed. So I'm still working to try to get this y prime by itself. And I would subtract 8xy cubed. That leaves me with 2x over 2 times 4x squared y cubed plus 1 minus 8xy cubed equals 12x squared y prime. And then I can divide both sides by this 12x squared y squared to get y prime by itself. So that's 2x over 2 times 4x squared y cubed plus 1 minus 8xy cubed all over 12x squared y squared. Okay, so that is the derivative. It looks a little bit messy. So I could write this as the 2's canceling out. So I've got x over 4x squared y cubed plus 1 minus 8xy cubed, and I'm going to write that over 1, and I can get a common denominator by multiplying by 4x squared y cubed plus 1 all over 12x squared y squared. I need to do that on the top and on the bottom to get that common denominator. That would be x over 4x squared y cubed plus 1 minus 32x cubed y to the 6th plus 8xy cubed over 4x squared y cubed plus 1 all over 12x squared y squared. So this would give me x minus 32x cubed y to the 6 plus 8xy cubed. This is actually a minus here. I need to distribute that minus. And then I can multiply by the reciprocal. So that gives me x minus 32x squared y to the 6 minus 8xy cubed. By the way, you don't have to do all this for me. I'm fine with the complex fraction. I just wanted to show you how to get rid of it. Okay, I think I found where I did it. So it looks like I changed this 3 to this 2 right here. So let me fix that. That should be a 3. And then looking at the answer key on the paper, it looks like they just canceled a factor of x out. X here, and x here, and x here, and 1x from here to get 1 minus 32x squared y to the 6 minus 8y cubed. And they distributed this 12 in the bottom to get 48 x cubed y to the 5th plus 12xy squared. Okay, so there it matches what's in the key. Thank you for checking out my videos. Have a great day.